Hello, this video is meant to give the sketch of the proof of the second derivative test for a function of two variables f of x and y. To do that, we start with defining discriminant and statement of the theorem of the second derivative test. The discriminant of f at a point a and b is in its domain is d of a and b equal to f sub x at a and b times f sub y at a and b minus f sub x y at a and b to power 2. Now, the second derivative test says if a and b is a critical point of f and all second partials f sub xx, f sub xy, f sub yy are continuous near a and b, then if the discriminant at the point is bigger than 0 and f of f sub xx at the point is bigger than 0, then the point is a local minimum. If the discriminant at a and b is bigger than 0 and f sub xx at the point is less than 0, then the point is a local maximum. If the discriminant at point is less than 0, then the point is a saddle point. If the discriminant at the point is 0, then the test is inconclusive. The second derivative test is based on the second degree Taylor approximation of the function at their critical points. We are assuming that at least one of the second derivative tests are not 0, so that d of a and b is not going to be 0. That's a part. If d of a and b is 0, test is going to be inconclusive. So let's start with Taylor expansion. If f of x and y have a critical point at a and b, and let f have a convergent Taylor series, second Taylor degree Taylor polynomial approximation of f at a and b looks like this. Again, a and b is the critical point. You can expand using Taylor series, but in this case we're expanding at a critical point. So it would look like this. Output z is going to be equal to f at the point plus f at the point, f sub x at the point times x minus a plus f sub y at the point times y minus b plus f sub xx at the point divided by 2 times x minus a to power 2 plus f sub xy at the point times x minus a times y minus b plus f sub yy at the point divided by 2 times y minus b to power 2. Notice, because we chose the point to be the critical point, f sub x at the point and f sub y at the point are going to be 0. Still, this Taylor polynomial approximation is very busy. So one way for mathematicians to make this less busy, to focus on what is happening truly with the polynomial, is to move the polynomial so the critical point moves to the origin. So a, b, and f of a and b move to the origin, and then you will have a neater and cleaner polynomial with the same properties. So if there's a local min, local max, or saddle point, it will be preserved by this transition, basically. So if you do that, you will get z equal to f sub xx at the point divided by 2x squared plus f sub xy at the point times x times y plus f sub yy at the point divided by 2 times y squared. Now, what we want to know is that what this Taylor approximation looks like, and that will tell us basically what the function looks like locally. And so I can completely ignore the coefficients relationship of the coefficients with the function for a little bit and just investigate any polynomial ax squared plus bxy plus cy squared, and figure out then how the a and b and c are related to the second partials of the function and how they are related to the discriminant. What we do in the next page is that we're going to assume that next two page, I guess, that either A is not 0 in here or B is not, or C is not 0. Because if both A and C are 0 and B is not 0, then Z, the Taylor polynomial, will look like Z equal to B times xy, which is a hyperbolic paraboloid saddle point. In this case, discriminant is negative, and basically the second derivative test works. So we can put this case aside and look at the case that, so to understand the shape in the other cases, let's start with when A is not equal to 0. In this case, Z equal to ax squared plus bxy plus cy squared, there are certain functions that are polynomials that we studied in this course, like paraboloid, hyperboloids, and so on, and cylinders, and so on. Now, because there is an x and y in there, they're not in their standard form. There are multiple ways of putting them in the standard form. But here, what I'm going to do is I'm going to complete this square to see if I can make any sense out of it. And even though it won't be the standard form, I may get more information out of this. So let's complete this square. As we know, I can factor out an a out of the first two terms, and then basically x plus whatever coefficient of xy is divided by 2 times y to power 2 is going to be the completing square, and as we are aware of, we will get extra the coefficient of y squared is not going to be cy squared anymore, because this expansion creates an extra term with y squared. So we have to subtract that from the original term of the y squared, and then the new coefficient of y squared is going to look like that. Now this gives me a little bit more information. Now I have this, even though it's not x squared, but then it's a combination of x and y to power 2 and plus y squared. And it sort of tells me, if I turn things around, and I may get a standard form of the polynomial, what it looks like basically. And so I'm going to go with the coefficient of this complete square and y squared, and see how they relate to each other. So the first case is that if the two coefficients they have the different sign, that is, if r times a, the coefficient of y squared, and the coefficient of first complete square, they are basically multiplied to be a negative value. In this case, we know that it's going to be a hyperbolic paraboloid, a saddle point. If the two coefficients multiply to 0, then basically, then the polynomial is a parabolic cylinder. and second degree polynomial doesn't give us enough extrema information, so we have to use another method. So second derivative test doesn't work. If the product of the two is positive, that means the sign of the two are the same. Then if this sign of A is if the sign of A is positive, then there is a paraboloid that is looking upward, and if the sign is negative, sign of A is negative, then there's a paraboloid that is looking downward. Now, we did all this with A not equal to 0. What's going to happen with C not equal to 0? And symmetrically, we do the completing the square. We get the same cases. We again get either a hyperbolic paraboloid or a case that we cannot recognize because the second derivative test is going to fail, and then we also get and we can also get either an elliptic paraboloid looking upward or elliptic paraboloid looking downward. So C not equal to 0 is very similar case as A. In mathematics, we typically don't show the cases similar to the cases for C not equal to 0. Instead, we say by symmetry or without loss of generality. Now, all of these, we were just talking about what R times A or R times C is. And now let's translate back to the Taylor polynomial. So in either case, R times C or R times A, the result is going to be AC minus B squared over 4, which translates in the Taylor polynomial. If we replace the value, it's going to be f sub xx at the point times f sub yy at the point divided by 4 minus f sub xy at the point to power 2 divided by 4. That's a fourth of the discriminant. So every time we were checking R times A or R times C, we were really checking the f-fourth of a discriminant. And then the other cases that we checked also, let's remember, were A equal to C equal to 0, where B was not 0 and discriminant was less than 0, which the Taylor polynomial gave us a hyperbolic paraboloid or a saddle point. So we checked all the cases, and they were all falling. They were all correct cases, basically. So let's take a look at all the different shapes that we get with our different polynomials. And in here, I set up the polynomial to be f of x and y equal to a x squared plus b y squared plus c xy, and a and b and c can change basically. So here I'm changing a little bit, and you can tell that d, which is the d that we set up in our notes, is positive in here, which is also the d, the discriminant that we set up in our notes, is positive, and it's the a is positive, and so you get a paraboloid looking upward. And then when you're, or elliptical paraboloid looking upward, then when you decrease a, you can see the paraboloid gets wider and wider, and then as we get closer and closer to 0, it becomes that cylinder that we were kind of hoping for. And then when a becomes negative, you can see the parabolic hyperboloid basically And then different knobs and whistles in here you can change. And again, shapes vary between those three shapes that you were expecting. The hyperboloids in one way or another, or the the paraboloids, or the cylinder. And that's visualization of what we just explained.